everyone, once again welcome back to my YouTube channel. This is Unit 3 Magnetic Effects of Current and Magnetism for class 12th, and we have already discussed Ampere's circuital law. Now it is time to talk about the applications of Ampere's circuital law, and today we are going to discuss these two applications. The first application is to find the value of magnetic field due to long straight current carrying solenoid, and we will have to apply the Ampere's circuital law in order to find the value of magnetic field due to current carrying solenoid. And the second application is similar, and the name of second application is to find the value of magnetic field due to toroid. So that means we are going to use Ampere's circuital law in order to find the value of magnetic field due to current carrying solenoid and due to current carrying toroid. So first of all, we will talk about the first application, that is magnetic field due to long current carrying solenoid. That means we are going to apply Ampere's circuital law in this case. First of all, we need to consider a long solenoid. A solenoid is said to be a long solenoid if its length is greater than the radius of the solenoid. So let us make a solenoid. Now we will consider a current flowing through this solenoid in this direction. So now, first of all, on the upper face of the solenoid, we will apply right hand curl rule. According to right hand curl rule, if we place the thumb of our right hand in the direction of flow of current and then we curl our fingers, we will find that the fingers are curling in the anti-clockwise direction. So the direction of magnetic field due to upper face is anti-clockwise. So let us mark an anti-clockwise direction of the magnetic field. And now we will again apply right hand curl rule to the lower face of the solenoid. Again we will place the thumb of our right hand in the direction of flow of current, and when we curl our fingers we will find that the direction of curling of fingers is clockwise. So let us mark the magnetic field due to the lower face in the clockwise direction. Now we can see that the magnetic field lines inside the solenoid are crowded, but the magnetic field lines outside the solenoid are less crowded and are far away. Therefore, it is considered that magnetic field inside the solenoid is quite strong, but the magnetic field outside the solenoid is negligible. Always keep it in mind that magnetic field outside the solenoid is not zero, but it is negligible. It is so small that it could be neglected. Therefore, the magnetic field inside the solenoid is always considered to be very strong because the magnetic field lines inside the solenoid are very crowded. Now this is a solenoid. Now we need to consider a closed path, because in order to apply the Ampere's circuital law, we always need a closed path. Without a closed path, we cannot apply Ampere's circuital law. So on this solenoid, we will consider a closed path which is rectangular in shape, PQRS, in such way. And now in order to apply the Ampere's circuital law, we have closed integral P dot dl. That means in order to apply Ampere's circuital law, we will have to write closed integral B dot dl is equal to mu naught I. But instead of writing closed integral B dot dl is equal to mu naught I in the first place, first of all, I would like to solve closed integral B dot dl. Let us find out the value of closed integral B dot dl. And in order to find this value, we will divide this closed integral into four parts. That is, closed integral B dot dl is equal to integral B dot dl P to Q plus integral B dot dl Q to R plus integral B dot dl R to S plus integral B dot dl S to P. Now we know that B magnetic field is in this direction, therefore the length PQ is also in this direction, that is the angle between B and DL is 0 degree. Hence we can say integral P to Q B DL cos 0. plus integral q to r b dl cos 90, because q to r is perpendicular to the magnetic field, therefore the angle between magnetic field and q to r is 90 degree, therefore cos 90, plus integral r to s b dl cos 0. Now magnetic field is in this direction, r to s is in this direction, therefore magnetic field and dl are acting along the same direction, therefore angle between them is 0 degree. So we will write cos 0 plus integral s to p b dl cos 270. Now the length s to p is in the downward direction and magnetic field is towards the right direction, therefore the angle between them is either we can say 90 or we can say 270 degree. Now we can solve it further and we have closed integral b dot dl is equal to integral b dl p to q plus 0, because cos 90 is 0, therefore for integral q to r we are having angle cos 90, so this is 0 because cos 90 is 0. Now talking about integral r to s b dl cos 0. Now r to s is in the outward direction, that is it is outside the solenoid, and we have already said that the magnetic field outside the solenoid is negligible, that is it could be neglected, therefore b is approximately 0, therefore integral r to s b dl cos 0 comes out to be 0, and cos 270 is already 0, therefore the term integral s to p b dl cos 270 also turns out to be 0, therefore we are left with closed integral b dot dl is equal to integral p to q b dl, and now it is time to solve this integral, therefore it is equal to, taking b outside, integral dl p to q, or we are left with closed integral b dot dl is equal to bl. So let us say this is our equation number 1, and now we have to apply Ampere circuital law, which we have not applied yet, and according to Ampere circuital law we have closed integral b dot dl is equal to mu naught into I, where I is the total current enclosed by the solenoid. Although we have considered I current is flowing through the solenoid, but this is not a total current because this current is passing through the number of turns. So in order to find the total current, let us say we are having I is the current flowing through the number of turns. If n are the total number of turns, small n are the total number of turns per unit length, and L is the total length of the solenoid, therefore total number of turns in the solenoid comes out to be n into L, that is small n into L is equal to capital N, which is equal to total number of turns. That means small n is indicating number of turns per unit length. Now we have closed integral b dot dl is equal to mu naught into total current, and total current is number of turns multiplied by I. So that is b is equal to closed integral b dot dl is equal to mu naught nli. So this is our equation number 2. Now this is the Ampere circuital law. Already we have solved closed integral b dot dl. So therefore equating equation number 1 and 2, we have bl is equal to mu naught nli. Now we can cancel L on both the sides, therefore we are left with b is equal to mu naught ni, which is the expression for the magnetic field existing inside the solenoid, and this expression is determined by using Ampere's circuital law. Talking about the second application of the Ampere circuital law, that is magnetic field due to toroid. As we have formed a toroid, so now let us consider that I current is flowing from the toroid and the radius of the toroid is taken as small r. Let us say we are having small n representing number of turns per unit length. I is the current flowing through the toroid. So as we already know that we will have to determine the total current, because in the first case we have considered the total current. So in this case also we will have to consider the total current. In order to find the total current, we need total number of turns. So here in this case, small n is representing the number of turns per unit length. So total length of the toroid is 2 pi r. but this toroid is containing small n number of turns per unit length. Therefore, total number of turns in this toroid is 2 pi r into n. Therefore, total current flowing through this toroid is total current I dash is equal to 2 pi r n I. So this is the total current. Therefore, closed integral B dot dl is equal to mu naught multiplied by total current. Therefore, closed integral B dot dl is equal to mu naught into 2 pi r n into I. So this is the Ampere circuital law. Let us mark it as equation number 1. Now, talking about the further part, now we need to solve closed integral B dot dl. Here in this case we are having closed integral B dot dl is equal to closed integral we will take closed integral B dl cos 0. Removing dot, we are having a angle between B and dl to be 0 degree. Why? Because magnetic field is always acting along the tangent, and also the length of the toroid, small portion dl, is also along the tangent of the circular toroid. So therefore we are having closed integral B dot dl is equal to B dl cos 0, or it is equal to B dl because cos 0 is 1. So solving this integral, we have to take B outside the integral. So we are left with closed integral B dot dl is equal to B integral dl, and when we will add up all the small lengths dl, we will come out with the B into 2 pi r. So closed integral B dot dl is equal to B into 2 pi r. This is our equation number 2. Now equating these two equations, we are having B into 2 pi r is equal to mu naught 2 pi r ni. Now cancelling 2 pi r and 2 pi r on both the sides, we are again left with B is equal to mu naught ni. So again we have found the expression for the magnetic field due to toroid, and in this case also the expression for magnetic field is mu naught ni. So that means the expression for the magnetic field either due to solenoid or due to toroid is same, that is B is equal to mu naught ni, which we have found with the help of Ampere's circuital law. I hope you have understood the articles. If yes, then do not forget to press like, subscribe and share button, and do press the bell icon in order to get the latest notifications on my videos.